Alright, in this video we'll be going through the 2015 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. An AC circuit has a variable capacitor, an inductor, and a resistor in series as shown below. Calculate the angular frequency of the supply. Alright, as we know, angular frequency is equal to 2 pi f, and we are simply given our frequency, and so we can just plug in our numbers, 50 hertz, and so therefore that's equal to 100 pi, or we can say that's equal to 314 radians per second. Show that the reactance of the inductor is 47.1 ohms. Alright, so we know the reactance of the inductor, the equation for that is XL is equal to omega L. Okay, we just found our angular frequency and that's equal to 2 pi f, and so that's equal to 2 pi times 50, and so we can say that's 100 pi. Okay, gotta keep it like this to keep whole values. And if we go up here, we can see we have our inductance of 0.15 henries. And so now we can simply plug in our numbers. We get 100 pi multiplied by 0.15 henries, and that's equal to 15 pi, or that's equal to 47.1 ohms. And as you can see, that's the value that we're trying to find. When the variable capacitor has a value of 1 times 10 to the negative 6 farads, the voltage across the capacitor is measured as 2.9 VRMS, and the current flowing through the circuit is measured as 0.656 ARMS. Okay, calculate the voltages across the inductor and the resistor, and draw a labeled phasor showing the voltages across the capacitor, inductor, and the resistor. Alright, so the voltage across the inductor is equal to I times the reactance of the inductor, okay? And the voltage of the resistor is equal to IR. Now, because this is a series circuit, the current measured at any point in the circuit is going to be the same. Now remember, even though the current is the same at all points, the current is still fluctuating. It's just that if we measure the current at a specific time, the current is going to be the same at all points in the circuit, okay? And so therefore the voltage of our resistor is equal to our current, which is 0.656, multiplied by our resistance, which is 10 ohms, okay, so multiplied by 10, and this gives a value of 6.56 volts. Alright, as for our inductor, it's equal to the current, so that again is 0.656 because it's the same at all points, multiplied by our inductance, which we just found as 47.1, and this gives a voltage of 30.9 volts. Now we are given the voltage across the capacitor as 20.9 volts, okay, and so from here we have the magnitudes of all our voltages, and so now we can make a phasor diagram from that. Our voltage of our inductor is going to be the largest, so I'm going to make that the largest vector. The voltage across the capacitor is 10 volts smaller, and so I'm going to make that vector slightly smaller, like so. And as you can see, the voltage across the resistor is much smaller, so we're going to make it something like that, okay? And so this is VL, this is VC, and this is VR. The variable capacitor is adjusted so that the circuit is now at resonance. Explain using physical principles why the current is now at a maximum, and calculate the value of the current in the circuit at resonance. Alright, so at resonance, the reactance of the inductor is equal to the reactance of the capacitor. And as we saw from our phase diagram, okay, I'm going to draw it out again. We have VL, and this is VC, okay, and this is our VR. As we can see, VL and VC are 180 degrees out of phase. Okay, and because the current is the same at all points throughout the circuit, we can apply Ohm's law to these values, okay, like so. And because the current is the same at all points, if we were to remove current from our phasor diagram, the shape of our phasor diagram will not change, okay? Now I emphasize the word shape because the value of each vector is different, okay? Obviously, this reactant vector will not have the same magnitude as the voltage vector because they're two different quantities, but the shape, the direction of the vector is the exact same. And so as you can see, the reactance of the inductor is 180 degrees out of phase with the reactance of the capacitor. And so therefore, if they're equal to each other, that means they will cancel each other out. And so mathematically, we can write that as XL minus XC is equal to 0. And so if they are equal to each other, that means 0 is equal to 0. Obviously. And because the equation for our reactance is equal to square root XL minus XC squared plus R squared, if this right here is equal to 0, we get Z is equal to square root R squared, and so therefore Z is equal to R. And as you can see, because now our reactances are no longer part of our impedance equation, therefore this is when the total impedance is at a minimum, and so therefore because V is equal to IZ, because our impedance is at a minimum value, and our voltage remains the same. Therefore, this is when we're going to have a maximum current. And so therefore, to calculate this current, we get I is equal to V all over Z. Our Z value is equal to the value of our resistor, which has 10 ohms of resistance, and we get a 12 volt source. And so we get 12 all over 10. And so this is equal to 1.2 ohms. A 9 volt cell is being used to charge a capacitor as shown below. At one point during the charging, the capacitor has a voltage of 6.4 volts, and the current flowing through the circuit is 0.208 amps. Show that the internal resistance of the cell is 12.5 ohms. Alright, so as we should know, the voltage across this capacitor is going to be equal to the terminal voltage of the cell, okay? Remember, terminal voltage is not the same thing as EMF. Terminal voltage is the voltage across the cell once we take the lost volts due to our internal resistance into account, okay? So this voltage across the capacitor is equal to our terminal voltage, and so therefore our terminal voltage is equal to 6.4 volts. Alright, and so therefore we can say our lost volts due to our internal resistance, which is going to be the voltage drop due to our internal resistor, so it's going to be this voltage drop right here, is equal to our EMF minus our terminal voltage, and so therefore we get 9 minus 6.4, and that's equal to 2.6 volts. And so therefore, V is equal to IR, and so therefore R is equal to V all over I. We know our voltage across our internal resistor, and so that's equal to 2.6 divided by the current throughout the circuit, which is 0.208, and so this gives a value of 12.5 ohms. The capacitor has air between its plates, and the plate separation is 2.26 times 10 to the negative 4 meters. If the capacitor has a capacitance of 2.75 times 10 to the negative 9 farads, what is the overlap area of the plates? Alright, so we know the equation for our capacitance is equal to epsilon naught times the permittivity of our dielectric times our area all over the distance. And so therefore we can rearrange for area, and we get CD all over epsilon naught times epsilon is equal to our area. Epsilon naught is the permittivity of free space, and that's equal to 8.85 times 10 to the negative 12 farads per meter. The dielectric constant of air is equal to 1 as given at the top, and so that is equal to 1. And our capacitance is given up here. And we also have the plate separation up here as well. And so now we can simply plug in our numbers. 2.75 times 10 to the negative 9 multiplied by 2.26 times 10 to the negative 4 all over 8.85 times 10 to the negative 12 multiplied by 1, and that gives an area of 0.07 meters squared. There we go. Alright, so this is a bunch of text that you can read yourself. I'm not going to read that. But essentially it just wants us to calculate this value of this resistor and therefore calculate the current throughout the circuit. And so the way we do that is by using this graph right here. And so therefore, because we know our time constant is equal to RC, because this is a circuit with a capacitor within it, okay? Therefore, we can find our resistance by rearranging for R, like so, as we have our capacitance, and therefore all we need to do is find the time constant. And how we find our time constant is we look at this graph, and we see when this 5 volts drops to 37% of its original value. And so in order to do that, we get 5 times 0.37, and that's equal to 1.85 volts, okay? And so 1.85 volts is roughly right over here. And so as you can see, this is roughly 70 seconds. And so therefore, because our time constant is 70 divided by our capacitance of 15, this gives a resistance of 4.67 ohms. Now, as you can see, this is slightly different to the 4.5 value. This is a common problem that usually happens when they tell you to interpret it from a graph, because you can interpret all kinds of values from the graph. As you can see, our line is pretty much on the 70 mark. You can see it just goes straight down to 70. However, that is because we decided that 0.85 is roughly over here. Now, if you go slightly more down, you can see that we end up right over here. And so the value that they have in the marking schedule is 68 seconds. Okay, so what I'm trying to get at is that they don't expect you to get exactly 68 seconds from the graph, because as you can see, these graphs aren't a huge scale. They're very hard to find the exact value. And so basically the range in which they allow is anywhere from 65 seconds to 75 seconds, okay? So even though you haven't proved that it's 4.5 ohms, if you show you have a time constant within 65 to 75 seconds, which we do, it's right bang in the middle, then they will allow your answer, essentially. And so therefore we know that V is equal to IR. As we can see from the question, the capacitor has been charged to 5 volts, Okay, and so therefore I is equal to V all over R, where our V is our 5 volts, divided by 4.67, and this gives a value of 1.07 amps. And if you want, you can calculate it using the resistance value that they give, which is 4.5, and you get 1.1 amps. So as you can see, it's pretty close anyways. One particular cell phone requires 6 times 10 to the 5 joules of energy to fully charge. A supercapacitor of 400 farads could be used to charge a cell phone that requires 5 volts with a resistance of 4.5 ohms. Use calculations to decide whether this capacitor would fully charge the cell phone within 5 minutes. In your answer, you should calculate the time taken for the capacitor to become effectively discharged, discuss whether the capacitor will release its energy within the 5 minutes, and calculate the energy released by the capacitor when it's discharging through the resistor, and compare the energy released by the capacitor with the energy that would be required to fully charge the cell phone. Let's see if there is even enough energy within the capacitor to even charge the cell phone. Okay, and so to find that, we go our EP is equal to half QV. And because we know Q is equal to CV, we can plug this into here, and we get half CV squared, okay? Now we know the voltage across the capacitor is 5 volts, and we know it has a capacitance of 400 farads. And so therefore, EP is equal to half our capacitance, which is 400, times our voltage, which is 5 volts squared. This gives a potential energy of 5,000 joules. Okay, now this is equal to 5 times 10 to the 3 joules, and as you can see, we require 6 times 10 to the 5 joules, okay, so we are way off. We do not even have enough energy within the capacitor to charge the cell phone fully, okay? So that ticks these points and these points off, okay? So we compared the energy in the capacitor to the energy that the cell phone requires, and we saw it didn't have enough energy, and we also calculated the energy within the capacitor. So now these top 2 points, the time constant, we know our time constant is equal to our resistance times our capacitance. We have a resistance of 4.5, and obviously our capacitance is still 400 farads. And so this gives a time constant of 4.5 times 400. This gives 1800 seconds. As we know, in order for a capacitor to be fully discharged, or effectively discharged, it must go through 5 time constants, and so T times 5 is equal to 9,000 seconds. Okay, and if we divide this by 60, we get 150 minutes, and divided by 60 again, we obviously get 2.5 hours, okay? So as we can see, even though it doesn't even have enough energy to charge the phone to begin with, even if it did have enough energy to charge the phone, it wouldn't even do it within the 5 minutes, because instead it will take 2.5 hours to discharge fully, okay? So it doesn't even meet both requirements. So we ticked off both of those points. Alright, well, it looks like I didn't screenshot the question properly, so you're gonna have to just deal with my amazing representation of NCEA question headings. Okay, so question 3. There are a number of techniques used to detect cars and bicycles waiting at traffic lights. The most common technique is the inductive loop circuit. State how an inductor stores energy. So an inductor stores energy in its magnetic field. And so you can write that in. One type of an inductor loop circuit is shown below. This circuit contains a 9-volt battery with an inductor of 1 times 10 to the negative 2 henries and a total resistance of 12.5 ohms in the circuit. Soon after closing the switch, the current is 0.26 amps. Find the voltage across the resistor and the voltage across the current, and therefore calculate the rate of change of current. Alright, well, we know that V is equal to IR, okay, and this is going to be the voltage across our resistor, and so therefore, as our current is 0.260 multiplied by our resistance of 12.5, this gives a voltage of 3.25 ohms. And so therefore, as this is a series circuit, therefore this 9 volts is spread across the 2 components, and so because this is 3.25, therefore the voltage across our inductor must be equal to 9 minus 3.25, and that gives a value of 5.75, and so this value right here is 5.75 volts. Alright, so as we know, the voltage across the inductor is the EMF of the inductor, and we know that the EMF of the inductor is equal to negative L, change in current, all over change in time, okay? And so this value right here is the rate of change of current, and so therefore, our EMF divided by negative L is equal to the rate of change of current. And so therefore 5.75 divided by 1 times 10 to the negative 2 is equal to negative 575 amps per second. Now what this negative is saying is that the rate of change of current is in the opposite direction to what the current is currently traveling in. Okay, now looking at the marking schedule, it looks like this question does not require that knowledge. okay? And so I'm pretty sure an answer that says 575 amps per second is also completely valid. A different inductive loop is constructed as shown below. When the switch is closed, the bulb is bright and then gets dimmer. Explain in terms of current why the inductor makes the circuit behave this way. So when the switch is initially closed, there is going to be a high rate of change of current, and as we know, the EMF being produced by the inductor is equal to negative L rate of change of current, okay, multiplied by the rate of change of current. And so if this value right here is high, and obviously the inductance of the inductor does not change during this time, we are therefore going to have a high back EMF. And so therefore, as the inductor and the light bulb are in parallel, if a back EMF is being produced by this inductor, it's almost going to be like this pathway is blocked off, right? Because as current goes through, it's going to be met with this back EMF, and this back EMF is going to prevent current from going through this pathway. And so therefore, all the current must go through this pathway through the bulb, okay? And as P is equal to I squared R, because all the current is going through the bulb, this is going to make the bulb glow bright. Okay. However, over time, as the rate of change of current, okay, as the rate of change of current starts to decrease, the back EMF produced by the inductor is also going to decrease, and it's going to decrease to the point where the inductor kind of just acts like an ideal wire. And so at that point, as this becomes an ideal wire, this becomes the path of least resistance, and so therefore more current is going to flow through this pathway than this pathway. And so therefore the bulb is going to get dimmer as less current is flowing through. And so you can write that in. Alright, so this is a bunch of writing that you can read. That's going to take ages to read, so I'm not going to do that. Alright, so answering this question, it's actually a very, very similar concept to Transformers. So if you haven't watched my video on Transformers, you can go check that out. But essentially, let's just look at Transformers for a second. We have a transformer. This is when we have an AC power supply and we just have a regular coil of wire. So, okay. When we have an AC power supply connected to a coil, this is going to create a magnetic field around this wire, okay? And because this current is going to be constantly changing, okay, and it's going to be constantly changing direction, the direction of this magnetic field is going to be constantly changing. And so because of that, the magnetic flux interfering with this coil right here is also going to be constantly changing. And as the EMF induced is equal to negative N delta phi all over delta T. If our rate of change of flux is high, therefore the induced EMF is also high, okay? So that's a very similar concept over here. We have an AC current going through our wire, okay? So that's constantly changing, and that's interfering with the metal rims of our bike, okay? And so that's going to do a very, very similar thing as over here. Because the magnetic field around our wire is constantly changing, therefore, when it interacts with the metal rim, there is going to be a high rate of change of flux, meaning there's going to be a high EMF induced into the bike rims. Now, once there's an EMF induced to the bike rims, there's obviously going to be a current being produced, and once there's a current being produced, there is going to be a magnetic field being produced around the bike rims. Now, due to Lenz's law, this magnetic field is going to be produced in a way that's opposite to the magnetic field that produced it, okay? So the magnetic field that's around the rims of the bicycle is going to be in opposite direction to the magnetic field that is produced due to the wire. And so these two magnetic fields are going to cancel each other out. And when this happens, the inductance of the circuit decreases. And so therefore, as it says over here, the traffic lights detect this reduction in inductance. And so you can write that all in. And with that, we're done. See ya.